Assalamu alaikum wa rahmatullah. Welcome back, and we are continuing our random signal theory lectures. And today we start a new chapter, chapter 7, which is entitled Sampling Distributions and Point Estimation of Parameters. I will come back to this title to explain what it means, but for now, let's start with my own note here. So this chapter is about a concept called parameter estimation. Now, what do we mean by parameter estimation? Let's set things up first. So similar to chapter 6, we assume that we have a population, and the population contains all information. It contains everything. So let me give you an example. Let's say we are interested in the GPAs of all second year university students in the world. So the population then would contain every single GPA of every single second year university student in the world. We might have millions of values here in the population. So this is one possibility, to know the population explicitly. Another possibility is that instead of knowing the population itself explicitly, instead of knowing every single GPA, we know the random variable that represents the population. So we might know the distribution of the GPAs. So we say the GPAs in general have a normal distribution or any other distribution. Again, we have a population that contains everything, and from the population we select a sample at random, and this is the key here in this chapter. We select a finite sample at random from the population. So what is the significance of this random selection? The significance, let's say, let me explain it through an example. Again, so the population was the set of all second year university students. The sample is the set of GPAs of a finite set of students. Let's say I choose your class to be the sample. Let's say we choose one of the sections that we have, section 11 or section 12, which means that the size of this sample is about 40 students. So in my sample I have 40 GPAs if I choose one of the classes. Okay, what about the random selection? The random selection means the following. Do I have only one sample available in the population, or do we have so many samples to choose from? We have a lot of samples that we can choose from. If the population is the set of GPAs of all second year university students, we have so many samples that we can choose from. I can choose your class to be a sample. I can choose the class next door to be a sample. I can choose the Circuits 1 class to be a sample. I can go to another college and choose a class to be a sample. I can go to the street and wait for the next 50 students who are second year. I ask them for their GPAs, and I have a random sample that was selected at random from the population. So we have a finite sample that we select at random from the population. Now, what do we do with this sample? We wish to do the following. We wish to do something called parameter estimation. Now, what is parameter estimation? We would like to infer, نستنبط, we would like to infer some unknown information about the population using this random sample. So this is a population, and let's say we have some unknown parameters here in this population. Using the small sample, we would like to approximate or infer these unknown parameters about the population, but using the sample alone. Let me try to give an example here, and as we proceed, things will become clear and we will end up with actual examples, and you will find it easy. But the main challenge in this chapter is to introduce this new topic to you so that you understand the main context here. So imagine, as an example, we have a population here. We have a population which represents the set of all second year university students GPAs. So inside the population I have a few million GPAs representing the GPA of every single second year university student in the world. What is the unknown parameter? I don't know mu. I don't know their average, the population mean. So the unknown parameter is the average of all GPAs in the population. What is the average GPA of all second year university students? That's obviously something unknown. How can we calculate it exactly? We can calculate it exactly either by knowing the population itself, so by really figuring out every single GPA in our population, or by knowing the random variable itself. Then we can do the calculation and get the expected value of x. But if this is not available, then the possibility then is to choose a sample at random, a finite sample at random, and Our task is to try to estimate or approximate that unknown parameter mu using the finite sample. So we try to estimate the average of the population as an example using the finite sample. This is our task, and to get there we have to make some definitions. So let's talk again about the setup. So x represents a random variable with mu and sigma square, so with mean mu and variance sigma square. So this random variable x represents a population, of course, so this may represent the set of all students' GPAs or the waiting time of all customers at a check-in counter or something like that. Now from this population, from this random variable, we assume that we choose a sample x1, x2, until xn. We choose a sample of size n at random from the population. Now in our context, if our population or random variable represents the GPAs of all second-year university students, what could a sample represent? If I choose your class to be the sample, then x1 is the GPA of the first student in the class, x2 is the GPA of the second student in the class, and so on. xn is the GPA of the last student in the class. So if we have 40 students, then our sample is of size 40, and we have x1, x2, x3, and so on until x40. This is a sample chosen at random from the population. Why do we say chosen at random? Because this is not the only sample available from the population. We could have chosen many other possible samples, and we say we choose one at random. Since this sample is chosen at random, so x1 represents the GPA of the first student in the class, but the class itself was selected from the population at random. So is this x1 something deterministic or something variable or something random? Is x1 as a variable, is it something deterministic or something random? It is random, of course. Why? Because we could have changed the sample completely. Instead of choosing our class, I could have gone to the computer science department and selected the operating systems class, and then x1 would be the first GPA of the student, the GPA of the first student in that class, which could have another value. So in other words, this x1, the first observation in my sample, so if x1, x2 until xn is a sample, then x1 is the first observation in the sample, x2 is the second observation in the sample, xn is the last observation in the sample, and obviously each one of them is a random variable because the sample itself is chosen at random from the population. So each xi, x1 and x2 until xn, each one of them is a random variable simply because they are selected at random. If they are random variables, then they have a distribution. So each one of the x1s may have a distribution, normal or any other distribution, but we don't know which one it is right now. Imagine that we apply a function on the sample itself. So once we select the sample representing the GPAs of our class selected at random, and then we apply a function on these observations. So again, if x1 is the GPA of the first student of the random sample, x2 is the GPA of the second student, and so on, xn is the GPA of the last student of our random sample. If we imagine that we apply function f on these observations, we call that function a statistic. So formally speaking, this course is called the book itself is called Applied Statistics and Probability for Engineers. The formal definition of a statistic is simply a function applied on a sample chosen at random from a population. So what are example statistics? Again, if x1, x2 until xn is a sample chosen at random, if I add all these observations up and I divide by n, what was that from chapter 6? We called it the sample mean. So as you notice, the sample mean x bar is just a function on the x1 and x2 and so on. That function, which is here in this case just adding them up, dividing by n. The sample mean is a function of the sample. That's why it's a statistic. So the sample mean is an example statistic. The sample variance is also an example statistic. So what was the sample variance again? It was the summation from 1 until n. So from 1 until the size of the sample, xi minus x bar all squared, and then at the end divided by n minus 1. This is obviously a function on the x1 comma x2 comma x3. So if I choose your class to be a random sample, I can calculate the sample mean, your average. I can calculate the sample variance of that random sample, and these two cases, sample mean and sample variance, are example statistics, simply because each one of them is a function of the random sample. Again, let's recap. Let's finalize this. So x1 comma x2 until xn is a sample chosen at random. So that's why each one of them, x1 itself and x2 until xn, each one of them is a random variable. Since each one of them is a random variable, then a function applied to these random variables is also a random variable. And because that function is a random variable, it has a distribution. What do we call this distribution in general? We call it a sampling distribution. So what is a sampling distribution? A sampling distribution is the distribution of a function of the random sample. Let me try to give an example. Again, our population represents the set of all second-year university students' GPA. So we have millions of GPAs inside our population. From that population, we choose your class at random. At random, we close our eyes, we choose a class at random, and then it becomes your class. So x1 is the GPA of the first student, x2 of the second, and xn is the GPA of the last student in this class that was chosen at random. Each one of these observations, x1 and x2, are random variables simply because they're not fixed, they're not deterministic, but they could have other values if another sample or another class was chosen. If I apply a function on these observations, like the summation divided by n, or like the sample variance, if I apply a function on the observations, that function is definitely a random variable itself, and because it is a random variable, it has a distribution, and the distribution is in general called sampling distribution. So before we proceed, let me go back to the title. The title was called Sampling Distributions and Point Estimation of Parameters. So now we understand the meaning of the first half of the title, sampling distributions, which is the idea of selecting a sample at random from a larger population, and since this sample is chosen at random, applying a function on the observations is also a random variable with distribution that we call a sampling distribution. Now the idea of point estimation of parameters, that's the idea of estimating unknown parameters of the population using the sample, and the word point here stands for the fact that in this chapter we would like to estimate the unknown parameter using a single value. So if we have a large population with all GPAs and we don't know the average mu, we would like to approximate this mu with a single value that we call a point estimate, and this is in contrast to providing a range as in chapter 8. So let me continue with our discussion and go back to the slides. So in the first two slides we will find exactly the information that I talked about using my own notes. So it is the idea of having a population. Usually it's a large population, like the set of all GPAs of all university students, or the set of heights of all men above 18 years old. Let's say we use that, so it means that our population has maybe billions of values. So the heights of every single man above 18 years old, and from the large population we may choose a smaller sample. Like I go to the streets and I wait for the first 20 men above 18 years old. I measure every one of them. I measure the height of every one of them. So I have 20 heights. So this is my sample that I choose at random. So what is the job here in this chapter is to do statistical inference. Statistical inference is about how to infer unknown parameters about the population or unknown information about the population using the sample that we choose at random. And what we cover in this chapter is called parameter estimation. Another possibility is called hypothesis testing, which is not covered in this chapter and not covered in this course. Now, let me go back to the definitions that we have. So this is the second time that we say the same thing in this video. x1, x2 until xn is a sample chosen at random from a larger population. So if the population is the population of the heights of all men above 18 years old, so x1 is the height of the first person chosen at random, x2 is the height of the second person chosen at random, and so on. Xn is the height of the last person chosen at random. Since these are heights chosen at random, this sample itself is chosen at random from the large population. It means that each one of the xi's, so x1 and x2, all of them, each of the xi's, each one of them is a random variable with distribution. Of course, if it's a random variable, then it has a distribution like normal, exponential, whatever distribution. So a function applied on these observations, so a function applied to the x1, x2 until xn values is called a statistic, which is definitely also a random variable, simply because these values are chosen at random. So if we apply a function, it's also a random variable, and its distribution has the name in general sampling distribution. So the distribution of the statistic is called in general sampling distribution. Some examples of statistics is the sample mean and the sample variance, and we talked about that. Now let me emphasize something here. Let me mention an example again. So again, our population is the set of all GPAs. I select a sample at random. Let's say our class that I select at random. So x1 is the GPA of the first student, x2 is the GPA of the second student, xn is the GPA of the last student in the class. Let's say I calculate the sample mean for our class, x bar. I calculate the sample mean by adding up all GPAs of the class, and then I divide by n. Now this will have a value. Is this value the same as the sample mean that I would get if I have chosen another class? So if I've taken the Circuits 1 class, one of the Circuits 1 sections, or any other class chosen at random from another college, and then I calculate the GPAs of that class, would it be the same as your average GPA? No, it's not. And this is just an indication that the sample mean is a random variable because it depends on which sample has been chosen. So this is some of the main definitions that we use here in this chapter. Okay, so let's continue our introduction in chapter 7 so that we understand the concept of parameter estimation. And what we are talking about here is just the main concept. So in this lecture, in this video, we are only talking about the main concept. In the next videos, we will be talking about specific mechanisms and specific techniques that we will use with specific examples. You will find it easy, inshallah. At that time, you will find it easy. However, we have to spend some time talking about the main concept. So imagine that x is a random variable with unknown mean mu. Mu is the population mean. It is the actual expected value of x of the random variable itself, and we know that the random variable represents a population. So let's say x is the random variable which reflects the GPAs of all second year students. I know that x is the random variable that represents the GPAs of the second year students. However, what I don't know is the mean mu. What is the average of these GPAs of all second year students? It's unknown to me and I don't know it. How can I calculate it exactly? I can calculate it exactly either by knowing x exactly. So let's say if I know that the GPAs have a normal distribution and I know all parameters, I know mu and I know sigma. In that case, this is known to me. Or I know that x has an exponential distribution and I know the parameter lambda. So everything is known. That function of x is known completely. If I know it exactly, I can calculate mu as the integral of x times f of x dx, or if it's discrete, the summation of x times f of x, and this is solved. However, if this is not doable, because x, basically I know it's a random variable but I don't know the function exactly, and also I don't know the population itself. So the population itself, I don't know it explicitly. So I don't have all GPAs of all second year students. So what is a mechanism for approximating this mu, this population mean? By taking a sample. So let's backtrack. X is a random variable with unknown mean mu. from this x, or from the population we select a sample at random, and that sample, let's call it x1, x2 until xn. So if our population was the set of GPAs of every single student, x1 is the GPA of the first student in the random sample, x2 is the GPA of the second student of the random sample, and so on until xn is the GPA of the last student in my random sample. If this is a sample of GPAs, how do you think can we estimate the population mean, the average of all students in the population? How can we estimate it? It is only intuitive. It is just intuitive. It looks like it makes sense that we can use the sample mean, which is the average of my sample, as an estimator to the average of everyone. It is just intuitive. So far, this is only intuitive. It just seems it makes sense. So I choose the sample mean x bar, which is equal to x1 plus x2 plus and so on until plus xn, and I divide by n, and I use that as a point estimator. So this is a definition here. Point estimator means what is the equation I will use, what is the formula I will use to estimate my unknown parameter. More scientifically, what is the statistic I will use? Remember, what was the statistic? The statistic is a function of the sample. What is a suitable function of my sample that I will use to approximate my unknown parameter? Now, it makes sense, since my unknown parameter is the population mean, the average of my entire population. It looks like it makes sense to choose the sample mean as a suitable statistic for my unknown parameter, a suitable statistic to approximate my unknown parameter. So I choose the sample mean x bar to be a point estimator for my unknown parameter mu. How do we calculate x bar? X bar is simply x1 plus x2 plus until plus xn divided by n. Now let's notice something. Are we using capital letters or small letters? Are we using uppercase x1 and x2 or lowercase x1 and x2? We are using uppercase x1 and x2, which is an indication that x1 is a random variable, x2 is a random variable, and so on until xn is a random variable. Why? Because this represents a sample that we select at random from the population, and this equation is only the general equation or the general statistic that we use to estimate mu, and we call it a point estimator. Now, once we agree that we will use the sample mean to approximate the population mean, once we agree to do that in general, we actually go and select an actual sample. So now let's decide to select, let's say, our class to be the sample that we have chosen at random. So I closed my eyes, I selected one of the classes at random. It turned out to be your class. Once I have fixed the sample, x1 and x2 and xn, each one of them can be represented by a lowercase, by a small letter, because the sample has been chosen already. Yes, we chose it at random, but after we choose it, x1 and x2 until xn, each one of them has a small letter. And if I calculate the sample mean, we can think of it as x bar. So let's say x bar is actually, we are using the lowercase letter. So the only thing that we mean here is that x bar here, the capital X bar, just means the sample mean of the random sample in general. But once we fix the sample and we calculate the sample mean, it becomes a number, it becomes a value, and we call it little x bar, small x bar, and this is the point estimate. Nothing fancy, folks, nothing fancy, my friends. The point estimator is simply the statistic that we use, the function that we have selected to approximate the unknown parameter in general. And since we have not chosen the sample yet, this is called a point estimator, and we just mean what is the formula or what is the statistic that we use. But once we have selected a particular sample, that capital X bar becomes a number, becomes a value, so we call it small x bar, and this is the point estimate of our unknown parameter. So what is the point estimator of the unknown parameter? It's the formula that we use to approximate mu. And what is the point estimate? After we apply the formula, after we substitute with our actual sample that we have chosen, this will have a value that we call the point estimate of mu. Now, the same idea can be generalized to other parameters. So unknown parameters are not necessarily the population mean mu, it could also be some other parameters. So examples of parameters in general, population mean mu, like the one that we have covered in the previous slide, but it could also be the population variance. So imagine that I'm saying the following: my population is the height of all men above 18 years old. The height of all men above 18 years old. I know that this population has a normal distribution. Assume that this population has a normal distribution, so the men's heights has a normal distribution with mean mu. Let's say I know mu 173 centimeters, so this is the average height of all men above 18 years old. Let's say I know that, but what I don't know is the variance or the standard deviation. What are the differences between the different heights? I don't know that. So sigma square is my unknown parameter. Let's even generalize further. So we have a population with any unknown parameter, mu or sigma square, or let's say if my population has a Poisson distribution, so my unknown parameter is the lambda, and so on. So any unknown parameter, let's use the letter theta, the Greek letter theta, to indicate any general unknown parameter. What is a general way? What is a general way to approximate or estimate this unknown parameter theta? So let me put you back on track. Let me come back to the context. X is a random variable with unknown parameter theta. So that theta could be any unknown parameter like mu, like sigma square, like lambda if you have an exponential or Poisson distribution, and so on. X is a random variable representing a population, of course, with unknown parameter theta. How can we possibly approximate or estimate this unknown parameter theta? Obviously, the only way that we have in this chapter is to choose a sample at random from the population. So if the population was all men's heights above 18 years old, so we say we will pick a sample at random, x1, x2 until xn will be a sample that we choose at random. It's not a specific sample, it's not a specific group of men, but it's a group of men that we select at random. And x1 is the height of the first man in the sample, x2 is the height of the second man in the sample, xn is the height of the last man in the sample that we will choose at random. Now, how can we possibly approximate the unknown parameter theta? In general, how did we approximate mu? We used the sample mean x bar to approximate mu. So let's call theta hat now. This is just the capital letter theta. What you see here is the capital letter theta, and we give it a hat because we want to say this is not the unknown parameter itself. No, the unknown parameter is unknown. Let's say sigma square is unknown. This is only an approximation to it. How are we suggesting to calculate this approximation? By choosing a suitable function of the sample. That's the only thing we have, and again, it's nothing fancy, but because this is a new concept, we are spending some time talking about it. My sample, which contains the height of the first person, the height of the second person, the height of the last person. What am I doing with these heights so that I can estimate theta? I have to choose a suitable function of these heights. So I have to choose a suitable statistic of my random sample as a point estimator of my unknown parameter theta. Once I decide to do so, I've chosen that function already. Now I go ahead and select a sample. So at random, I close my eyes and I pick, let's say, 50 heights of 50 men that I choose at random. So I have x1, x2 until x50, but each one of them has a value now. Each one of them is a number. And if I apply the function h, I have theta hat, which has a value now. It has a number, basically. It is a number. So this is the capital letter theta, which just represents something random. In general, it's a function of the random sample, but once I fix the sample, I apply the function, this capital theta hat will have a value that I give the symbol small theta hat, and this is the point estimate of the unknown parameter theta. So what you see here in this slide is just a generalization of what you have seen here on that slide, but the only difference is that our unknown parameter was just the population mean mu, and when the unknown parameter was the population mean mu, the function that we have chosen to estimate was nothing but the sample mean, and the estimator theta hat was called x bar because we know that the sample mean, we use the symbol x bar for it. So this is the idea. Now, so that we stress this information, let me just mention some examples of some unknown parameters that may arise in engineering applications, and also the way that we can estimate them. This is the idea of this chapter, so we're not doing any calculations yet. But using this general information, we will come back in the next video, inshallah, to talk about things more specifically and talk about more specific examples. Now, what could be an unknown parameter? The average, the mu, the average mu, or the population mean could be an unknown parameter. Like if our population is the set of all GPAs of all second-year university students, if I don't know the average of this population, then mu is the unknown parameter. Again, if my population was the set of heights of all people above 18 years old, and I don't know the average, then the unknown parameter is mu. What else could be an unknown parameter? The variance or standard deviation, so sigma square or sigma of a population. So again, if my population is the set of heights of all people or all men above 18 years old, this is my population. So if I want to calculate it explicitly, we have billions of values inside this population. But I don't know sigma square. I don't know the standard deviation of the population. So this could also be an unknown parameter here. The proportion P of items in the population that belong to a class of interest. This sentence might seem confusing, but it's really easy. And I'll use that as the last example today. What is this unknown parameter exactly? Now let me go back to the GPA example. Imagine that my population contains the set of all second-year university students' GPAs. So let's say we have millions of students in the world who are in the second year in some university, and the population contains all of their GPAs. Let's say I have a class of interest. I don't know what is the percentage of all students who have a GPA above 3.5. What is the proportion or percentage P of all university students who have a GPA above 3.5? Is it only 5%? Is it 7%? Is it 10%? Is it 50%? If I don't know, then this is my unknown parameter. So let's say for the first three parameters, the population mean, the average of the entire population, the variance or standard deviation of the actual population, or the proportion basically of those items in the population that belong to a specific class. Like what is the proportion or percentage of students who have a GPA above 3.5. Now how can we estimate these unknown parameters? Again, it is intuitive. It looks like it makes sense. It looks like a good idea to estimate these parameters in the following way. So if my unknown parameter was mu, the population mean, it looks like it makes sense to use the sample mean, like the average of the small sample, as an estimator to the population mean. So that mu hat, that's not the actual population mean, that's not the actual average of all university students. No, this is only an approximation. So we use the hat just to indicate that this is not the actual value of the unknown parameter. No, this is only an approximation, only an estimation. And we say mu hat, the estimator of mu, is equal to x bar. So we use x bar, the sample mean, the average of the small sample. Of course, these estimators are based on choosing a sample from the population. So if the population is all students' GPAs, we choose a sample from these students at random. Let's say we pick 50 students at random somehow. And if x bar is calculated, so the average of the small sample itself, we can use it as an approximation to the average of the entire population. Is this something good or bad to be done? How good is this estimator? We will learn this in the remainder of this chapter later, inshallah. But for now, it looks like this is a good idea, right? Because this is a mean and this is also a mean, but this is the mean of the entire population. This is the mean of the small sample. Now, if my unknown parameter is sigma squared, so my population contains all students' GPAs, and what the unknown parameter is sigma square, the actual variance of the population. It looks like we can approximate or estimate this unknown variance using the sample mean. So again, I choose a small sample at random from the population. I calculate S square using our information in chapter 6, which is the summation of xi minus x bar all squared and then divided by n minus 1. Now I have S square. I use this S square as a point estimator of the unknown parameter. Now finally, for that proportion P, imagine that my population contains all university students GPAs, all world university students GPAs, let's say even all second year university students in the world. This is my population. Now what my unknown parameter is this percentage P, which represents what is the percentage of the world students who have a GPA above 3.5. How can we possibly estimate this? What makes sense? It looks like if we choose a small sample, let's say we choose your class as the random sample. So we have 40 students. For each student, I have a GPA. I ask you, what is your GPA? Or I check the system. I have x1, x2 until x40, which is all the GPAs in our class that we have chosen as a sample at random. Now, among these GPAs, I calculate x, which is basically how many students among this sample who have a GPA above 3.5. Let's say from among the 40 students, I check how many of you are above 3.5. I find it is 4 students. I find it is 4 students who have a GPA greater than 3.5. I divide 3 by 40. 3 divided by 40, which is basically what proportion of students are above 3.5 in our sample, not in the whole population, only in our sample. I use this as an estimator to the actual P, which is the proportion of students above 3.5 in general. Again, how did we calculate, how did we estimate that unknown proportion P of students above 3.5 in general? We took a sample at random. Let's say this sample was your class. I checked who is above 3.5. I found it is 3 students. As an example, I divided by the size of the sample by 40, so 3 over 40. What does this represent? It represents the fraction or the proportion of students above 3.5 GPA only in our sample, not in the whole population, only in our sample. But I use it as an approximation or as an estimator to this unknown parameter P. So next time we will continue with another topic called the central limit theorem, a very powerful theorem in statistics. And until we get there, Assalamu alaikum wa rahmatullahi wa barakatuh.